Whenever you go on holiday, I'm sure you struggle with this moment when you have to pack your bag. There's probably a lot of things you want to carry, but there's only a limited space. Luckily for us, humans are quite good in recognizing shapes, and we have a pretty good intuition if something is going to fit in a given space or not. However, this is not always the case, and this is certainly not the case for computers. Think, for example, about online shopping delivery. Chances are that if you've ever made a combined order, you received an oversized box. This could be either because the person doing the packing didn't have much time to play around with the items, or simply because a computer did a poor estimation of the box size needed. This is where my research comes in. My thesis is about developing the necessary tools and mathematical models to help solving the packing problems automatically. Traditionally, researchers have been able to pack simple shapes, such as boxes or spheres, but they have struggled with more complicated ones, such as those that have concavities or holes. I have chosen not to pack the original shapes, but to approximate them by something called voxels, that are the 3D equivalent of pixels. This is what you see over there in the left. The good thing about them is that we can make the representation more accurate simply but by making them smaller. Using voxels, I was able to develop something called the no-fit voxel. Let's look at this example here in the middle. If we have a rubber duck and a stick, we can create the no-fit voxel of the two simply by moving the stick around and marking it red when the two pieces overlap. If we do that, we will end up with that red shape over there, which looks like the addition of the two. This is important because it tells us all the relative positions of the pieces that are not valid. And we can pre-calculate this beforehand, prior to the packing. Using this, I was able to develop exact mathematical models and also approximate algorithms that can work efficiently with any kind of shape, even if it has concavities or holes. Currently, I am using these approximate algorithms to solve packing problems where the objective is to minimize the height of a container. This is what you see on the right over here, where I've packed all those shapes in a container where the base is fixed and the height has to be minimized. This has applications, for example, in the 3D printing industry. However, I think that the most interesting part of my research is its wide applicability. This could mean that in your next online order, you will be getting a box of an adequate size. And this means we are saving money, cardboard, and therefore trees, and ultimately the world. Thank you very much.